Hello everyone. I'm sorry that I had to be gone today at a teaching conference on the East Coast, but I've recorded the lesson so we can continue the show. Yesterday we were working on the second section of 12.6. If you would please have out your homework for it, and I've got the answers up here. I'm just going to read them off so you have a chance to correct yours, know if you did them right, mark any you missed, circle any ones you'd like to ask a question about when I'm back. So have out your homework from 12.6. It was the second day we were working on it. Yesterday we were working on combinations and permutations. If we need to pause the video now while everyone has it out, we can do that. Otherwise, I'm about to read off the answers. Okay, so question 2 was a combination. Question 3, that was a combination as well. Question 4 was a permutation. The difference between the two is combinations are used when we're counting things where order does not matter, and permutations are used to count items when order does matter. Question 20 was a combination. Question 22 was a permutation. 25, there were 1,320 ways. 32, A was 495, B was 24. Question 10 was 1 out of 30,240. Only one way to be successful, and there were 30,240 options. 36 was 50.4 seconds. 38A was 54,264. B, first part was 21, then 56, then 6. C, 7,056. And D, there was about a 13% chance. Question 40, 330. So, like I said, circle any ones you'd like to ask a question about when I'm back. Otherwise, if you would please, have out your note packet for section 7 in chapter 12. So 12.7. As you're doing that, I am just going to talk through real quick one of our SAT, ACT prep questions that we like to look at every now and then, so you can kind of see what the SAT and the ACT, the questions that they ask. This one comes from the very beginning of algebra / their pre-algebra section, just understanding how functions and linear relationships work. It's a pretty straightforward question. Honestly, it's just interpreting the graph and the context. They say admission to the school fair is $5 and each ride is the same price as any other ride. The graph below shows the total cost for a person for admission and rides as a function of the number of rides paid for. One of the following is the price of a single ride. Which one is it? And so they give you the cost of admission, and you see that in here because that is your y-intercept. And then if they do one ride, it's somewhere between $5 and $10. If you do two rides, it's something just below 10, maybe 9. The easiest point to use is probably this 5. So if I look at the 5, then the reason why it's easier is because it's on an intersection. It's at $15. What they're essentially asking for here is the slope. 0 rides cost $5 and 5 rides cost $15. I see if I subtract my y's, 15 minus 5, that's a $10 increase. It's a $10 increase for 5 rides. And if I simplify, I will see that ends up being $2 for one ride. So a single ride is $2. It's essentially asking for the slope of the line. So there we are. Today what we're working on is calculating the probability of what we call compound events. Compound events are when there are two events that we're discussing, compound meaning multiple. So here's a situation, an example. Mr. and Mrs. Smith have 2 children. What is the probability they had a boy and then they had a girl? So there are 2 ways that I could do this. I could just list all of the possible 2-child families and find the one where there was a boy and then a girl. So that's option 1. It's kind of the longer way to do it, but we'll do it, and then we'll talk about the more efficient technique. So I list all of the 2-child families. So you could have boy, boy. You could have boy, girl. You could have had a girl and then a boy. Or you could have had a girl and then another girl. And if I go looking, I'm looking for the one where they had a boy and then they had a girl, and that is this one. And that is a 1 out of 4 chance. So there's one way of doing it. I list what's called the sample space, and I select the appropriate one depending on the context. Option 2 is this. I want to know the probability of a boy and then a girl. And something we're going to learn is in probability, when we use the word and, it actually implies multiplication. I need this and I need that second thing to occur, so they're interconnected. So I'm going to need to multiply those two things. And the probability of a boy is 1/2, and the probability of a girl is also 1/2, and 1/2 times 1/2 is 1/4. So the likelihood of having a boy and then having a girl is 25%. So that's the more efficient way of doing it. I find the probability of each of them and I can simply multiply. The reason I can do this is because these compound events are independent. And we know just from basic English, independent meaning free, that one does not affect the other. The fact that one occurs doesn't change the probability of the second one's outcome. So that's a little introduction to what we're going to be working on. The 4 vocab words for the day are the following. We're talking about compound events. Those are events or situations made up of 2 or more simple events. A joint probability is the probability of compound events. The joint meaning that they're connected in some way. We're going to be using the English words and or, and that turns out to be connecting the probabilities by either multiplication or addition, respectively. Independent events are 2 events are said to be independent when the outcome of one has no effect on the other. Dependent events are the exact opposite. The fact that one occurs depends on the other. So 2 events are dependent when the outcome of one has an effect on the other. It inherently changes the probability. So the mathematical rules for these things are as follows. In words, for the probability of independent events, if 2 events, say A and B are the 2 events, in our last example it was having a boy and then having a girl, then the probability of both events occurring is the product, the multiplication of the probability of A and the probability of B. You see the word and used, and like I said, and implies multiplication. So I just need to take the probability of A and multiply it by the probability of B. And that would be if the events are independent. Nothing changes between probability of A and B because the fact that A has already occurred doesn't change the fact, or doesn't change the probability of B occurring. However, for dependent events, that's not the case. If 2 events, say A and B, are dependent, then the probability of both events occurring is the product of the probability of A and then the probability of B after A occurs. And so the first part is the same, probability of A, because that's the first thing occurring. There's nothing that could have happened that would alter that thing's probability. But the thing that's different is that we are now talking about the probability of B following A, probability of B given that A has already occurred. Next year you'll more formally study these types of things. You'll study something called a conditional probability. Right now we're just talking about dependent events. It's more vocabulary based. We still have the word and implying multiplication. The difference here is we're not talking about just the probability of B, we're talking about the probability of B given A has already occurred, following A. Okay? Let's look at some examples just to help clarify this topic. So, our goal here is just to state whether each set of compound events is independent or dependent, and then calculate the probability. So, situation, you roll 2 dice, find the probability you roll a 6, and then you roll an odd number. Well, some of this is just life experience. Hopefully you know the fact that you roll 1 dice, it should have no effect on the second one. So we just know from real life and kind of contextual clues that these 2 events are independent. What 1 dice does will not change what numbers might occur on the second one. So because of that, then I know the probability of getting a 6 on the first and an odd on the second is simply just going to be the multiplication of those 2 things. I need the probability of getting a 6, and then I multiply it by the probability of getting an odd. I don't need to write odd following 6 because they're independent. The odd isn't affected by the fact that the first one might have been a 6 or might not have been a 6. The likelihood of getting a 6 on a die, we know there are 6 sides to a die, only one side has a 6, so it's 1/6, times the probability of having an odd. On a die there are numbers 1 through 6, the numbers 1, 3, and 5 are odd, So there's a 3 out of 6, or you could do a 1/2 probability of getting an odd. 1/6 times 1/2 is 1/12. So there's a 1/12 chance. You could write it as a decimal if you want. It's about 8.3% chance of getting a 6 and then getting an odd number. That's an independent set of compound events. Okay. Second one. Now let's go. A lot of the times we like just to use rolling dice and cards. Cards are a good example of when these types of probabilities need to be known. You draw 3 cards from a deck, and the important part about this description is they use the phrase without replacing. Find the probability of getting the 3 cards in the following order. So the probability, your first card is a club, your second card is, your first card is a diamond, your second card is a club, and your third card is not a club. So there's a couple of things you might need to know. So if you've worked with cards, you've played card games before, you might know some of these things. If you don't, then you're about to learn a little bit, I guess, about cards. There are 4 suits to any deck of cards, standard deck. First suit is the hearts, and there are 13 of those. Second suit in red are the diamonds, and there are 13 of those. The numbers 2 through 10, and then there's Jack, Queen, King, and Ace. So 9 numbers and 4 non-numbered cards. There are also spades, and there are 13 of those. And the last one are your clubs, and there are 13 of those. So if you didn't know that about cards, well, now you do. Okay. We want to know what's the likelihood that we draw 3 cards in the following order. And the key is, though, we are not replacing them. They do not go back into the deck. That's going to mean, because they don't go back in the deck, these events are going to be dependent. It depends on what was drawn prior, because it will change the probability of the later events. You know, there are less clubs maybe in the deck. So these are dependent. So that means if I want to find the following, I would do this. I want to find the following probability. So I would find the probability of first getting a diamond. Probability of getting a diamond, and then I'm going to need to multiply it by the probability that the next card is a club that is following a diamond. I'm going to use little symbols because I think I'm going to run out of room. Because the first card was a diamond. And then the last one I need is I need the probability of not a club following the first 2 events. And the first 2 events were we had a diamond and a club. And these second 2 are going to be affected by the first one. So probability of diamond on the first draw, we know, well, that's just going to be 13 out of 52. There are 13 diamonds, 52 cards. Now I multiply by probability of getting a club following the first one being a diamond. Well, there are still 13 clubs in the deck. However, because it wasn't replaced, there are now only 51 cards in the deck because that first one was a diamond. And then the last one, what's the probability of getting not a club following the first 2 draws? Well, there are now, originally there were 13 plus 13 plus 13. There were 39 not clubs in the deck, but my first draw was a diamond, so I have 1 less card. So I actually only have 38 not clubs in the deck. And because I've already drawn 2 cards, there are now only 50 cards left in the deck. So I need to multiply these. And how do I multiply fractions? I multiply straight across. So I do 13 times 13 times 38. I end up with 6422 up top, and down below I get 52 times 51 times 50. It turns out to be 132,600. And I take those 2 numbers and I divide to get my probability. Turns out to be about 4.8% chance, 0.048. Like I said, about 5%. And that's an example of a dependent event. Okay, so now we kind of understand hopefully a little bit about independent and dependent events. I'm going to give you a chance to try it. So your 2 situations, let me zoom it out a little bit so we can see a little easier. Okay, your situations are as follows. So on the whiteboard, I'm going to ask the video to be paused in a second. I want you to try. So here's situation number one. They actually use an advanced idea of this when they're searching for if like a hiker got lost or if a plane went down in an area. They use a more advanced model of what's going on in question one, but you can do the beginning model that's done in question one. So question one, a search and rescue team believes there's a 40% chance that a plane actually went down in this area. What's the likelihood that it went down in this area and landed in the forest? Question two, state whether the following is independent or dependent, and then calculate the probability. You flip a coin 3 times. What's the probability of getting tails 3 times in a row? So if you would please pause the video now, come back after maybe a minute and a half, should be a good amount of time. Check with your neighbors since I'm not there to directly help you. And after the video has been paused for that time, we'll unpause it and I'll talk our way through it. Okay, so welcome back. Let's talk about this. So I need the probability that it goes down in this area and landed in the forest. So I know I need to find, this is a dependent event because the fact that it went down in this forest area depends on it landing in the first area. So I need probability of it landing in this area, so probability of going down in the area, multiplied by the probability of the forest given that we're in the area. So the first thing is, what's the probability we went down in the area? Well, that's a 40% chance, so 0.4. Then it says the word and. Because it uses the word and, that's why we're multiplying. And I multiply by, what's the probability that we landed in the forest, or the plane did, given that it's in this area? Well, I see the forest looks to be about 50% of that area, so 0.5. So we need 40% times 50%. 0.4 times 0.5 is going to be 0.2. So there's about a 20% chance that it went down in that area and landed in the forest. So that's an example of a dependent. Down below, state whether it's independent or dependent. Hopefully you know just from life that if you flip a coin, those are independent events. The fact that one came up heads has no effect on the other coming up heads or tails. So this is independent. So all I need to do then is find the probability of getting tails 3 times in a row. I need tails the first time, and I need to multiply by tails the second time. I'm just going to use a T now to represent tails, times the probability of getting tails again. And I know there's a 50% chance for each one, 1/2. So I have 1/2 times 1/2 times 1/2, and that's going to turn out to be an eighth. Eighth is about 12%. So it's about a 12% chance you flip a coin 3 times and you get tails 3 times in a row. Actually, the probability of getting heads 3 times in a row would also be then 1/8 as well. Okay? So that's the first part. Second part has to deal with what it's called mutually exclusive events. Mutually exclusive events, now we're talking about 2 events, but we're not talking about 2 events occurring one after the other. We're actually talking about 2 events that couldn't even occur at the same time. Mutually exclusive means that there is no overlap. If I drew a Venn diagram of these 2 events, they share nothing in common. It is impossible for them both to occur at the same time. So 2 events, A and B, are mutually exclusive. Then the probability of one occurring or the other occurring is just the simple addition of them because they share nothing in common. There's no overlap. So that mutually exclusive means 2 events that do not occur at the same time. Example. Let's say you're playing Monopoly. I understand in Monopoly you really roll 2 dice, but for the model to be a little simpler, let's just imagine that we would just roll 1 die. So you're on Park Place right here. And what is the probability you land on or pass go? Well, in order to land on or pass go, you need to roll a 1, 2, a 3. So anything that's a 3. So you need to, at least a 3 in order to land on or pass go in order to collect a little bit of money. So the probability, and like I said, we're just going to imagine just rolling 1 die, so our model is a little simpler, of getting at least a 3. At least a 3 would be probability of getting a 4, or sorry, go back. Probability of getting a 3 or a 4 or a 5 or a 6. That's what it means to be at least 3. It means 3 or more. And because we're using the word or, we're going to be adding. So I need the probability of 3 plus the probability of getting a 4 plus the probability of getting a 5 plus the probability of getting a 6. Each one of those is a 1/6 chance. So I have 1/6 plus 1/6 plus 1/6 plus 1/6 chance. If I add all of those up, I have 4/6 and 4 6 is 2/3. So I have a 66% chance of landing on our pass and go. This is because it's a mutually exclusive. We're using the word or. Or in probability implies addition. We'll try one more. Let's say you're on community chest. So you're right here. You're the dog. What is the probability you land on free parking or you land on the chance? So you would need to roll a 3 or a 5. And because we're using the word or, it's going to be simply addition. Probability of 3 plus the probability of 5. 3 is a 1/6 chance. 5 is a 1/6 chance. So we get 2/6, or a 33% chance, 1 out of 3 chance that I land on one of those two spots. Okay? The opposite of mutually exclusive is going to be the following situation. So what if I asked you to find the probability of drawing a card from a deck and asking you the probability of drawing a 2 or a diamond? Are these mutually exclusive? Well, let's just try it. Let's say I do it like we were doing before. I want the probability of getting a 2 or getting a diamond. I'll just use D to represent diamond. And I know or means addition, so I do probability of getting a 2 plus the probability of getting a diamond. The probability of getting a 2 we know is, well, there's 4 2s in the deck, one for each suit, so 4 out of 52 plus what's the probability of getting a diamond? We talked about there are 13 of each suit, so 13 out of 52, and I add those up and I would say, well, there's 17 out of 52. There's a 17 out of 52 chance that I get a 2 or a diamond. But if I go over and actually count all of the possibilities, well, how many 2s are there? There are 1, 2, 3, 4 2s. And how many diamonds are there? There's 1, 2, 3, 4. There's 13 of those. But the problem is we counted this 2. We counted it twice. So the probability of getting a 2 or a diamond isn't going to be 17 out of 52. If I count up all of the things that were successful, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, it's 16. It's only 16, and the reason why is because I double counted this 2 of diamonds. I counted it as a 2 and I counted it as a diamond. So I can't just simply add the two things together if they are not mutually exclusive. What I actually need to turn out to do is I need to subtract out whatever they overlapped. So what I need to do instead is not what we did up here. It's not quite correct. What I need to do instead is I need to find the probability of getting a 2 plus the probability of getting a diamond, and I need to subtract off wherever the overlap occurs because I double counted those. And if I do that, 4 plus 13 out of 52 minus 1 out of 52, I'm going to see I get the correct answer, 16 out of 52. So if I have events that are not mutually exclusive, how does the formula change? Well, I still add the 2 original events, but I need to subtract off where they overlapped, where I could have gotten a 2 and a diamond. And that's known as the probability for events that are not mutually exclusive. So if 2 events could occur at the same time, like the 2 and the diamond. If 2 events, A and B, are not mutually exclusive, then the probability of either A or B occurring is the sum of the 2 individual probabilities, and I need to subtract out the probability of both of them occurring, because that was the overlap. Examples. Let's say I draw a single deck from a card, or a single, opposite way around, card from a deck, and I state whether each is mutually exclusive or not, and then I'm going to calculate. So let's say I draw a single card from the deck. What's the probability of getting a 7 or getting a jack? Well, I need to ask myself, is there any way to get a 7 and a jack if I'm drawing just a single card? No. These 2 events are mutually exclusive. There's no overlap. There's no such thing as the 7 of jacks. So all I need to do is do the probability of 7 plus the probability of a jack. And because there's no overlap, I don't need to subtract anything off. These are mutually exclusive events. Probability of getting a 7 is a 4 out of 52. The probability of getting a jack is also 4 out of 52. So I would say it's 8 out of 52. If I simplify 8 out of 52, divide them both by, I could divide them by 2 first, and I get 4 out of 26, and then I notice I can do it again. I end up getting 2 out of 13, because I could have divided them both by 4 at first. So 2 out of 13 chance. Second one, what if I then said I'm going to draw a single card and I want to know what's the probability of getting a spade or a 9? These are not mutually exclusive because I could get a spade and a 9. We call that card the 9 of spades. So I need to do probability of a spade plus the probability of a 9 plus the probability, or not plus, subtract off. I need to subtract off the overlap, the 9 and the spades. The probability of getting a spade is 13 out of 52. Probability of getting a 9 is 4 out of 52, and then we need to subtract off the 1 that we counted twice, which was the 9 of spades. We counted it once as a spade and once as a 9, and we get our 16 out of 52. If you divide by 4, we're going to end up getting, well, actually, if I just type in 16 over 52 on the calculator, I get 0.307. If you ask it to simplify it, you end up getting 4 out of 13 if you want to simplify it. So 4 out of 13 chance. And that's how mutually exclusive and not mutually exclusive events work. I'm going to ask you to try one last one, and that'll be it. So on the whiteboards, if you would, please pull them out. Take 1 minute, pause the video, give yourselves a chance to try it, come back after a minute, and I'll go quickly over it, and then that'll be it. So pause the video now, please. Okay, welcome back. The situation was as follows. Quality control tests TV manufacturers and determined that 3% of TVs have video problems, 1% experience audio problems, and 0.2% experience both video and audio. What is the probability a TV will experience either video or audio? So the first thing you should ask yourself is, are these two events mutually exclusive or not? And these are not mutually exclusive events. The reason why is because we know 2% of TVs have both video and audio. They could have both problems. So what's the likelihood of having video or audio? I need to take the probability of having a video problem plus the probability of having an audio problem. I need to subtract off the overlap because that got counted in both of them. So I end up with 0.03 plus 0.01, which is 4%, minus 0.002, which is 0.2%, and I end up with 0.038, or about 3.8%, have either video or audio problems. And that's it. Rest of the time for today is for you to work on the homework. Answers for it are right here. If you want to pause the video and just leave it on this screen, then you can check your answers as you work. That's all I have for you. Thank you very much, and have a good day.